All right, welcome everybody to our Let's Talk Meshing webinar. Today we're going to be covering some new features in Pointwise version 18, and two of which are unstructured quad and hex meshing. My name is Travis Kerrigan. I'll be the host of today's webinar. I'm an engineer here at Pointwise. And for the Q&A portion, I'm going to be joined by Carolyn Weber. She's the manager of our technical support team. So if you have any questions, please feel free to type them into the questions dialog box, and we'll get to them at the conclusion of the webinar. Carolyn will pop on and answer those questions at that time. Also note that a recording of this will be available. We'll give you a little bit more information about that at the end of the webinar. And then lastly, kind of the flow of events for this webinar. I'm going to cover a few of the features in slides, but then we're going to jump right into a live demo where I mesh an entire aircraft from scratch using some of these new features that we'll be talking about. So please be sure to stick around for the entirety of the webinar, as you're going to see some really neat things with Pointwise version 18. So what's new in Pointwise version 18? And the answer to that question is there's a lot of stuff in Pointwise version 18. It represents one of the largest releases that we've had to date. A lot of new technologies in here, a lot of new examine metrics and export utilities and things like that. But we're just going to focus on four main features: mixed cell domains, mixed cell blocks, the ability to draw and use primitive shapes, and create grid sources for refinement in the volume. Now, I know that quite a few of you are Pointwise users, but I also know that there are quite a few of you who are not Pointwise users or who haven't used our software in the past. So just a brief introduction to our terminology, because I'm going to be using it a lot throughout the webinar as we work through the demo. Pointwise is a bottom-up mesher, meaning we start at the geometry, we build grid curves, we build surface meshes, and then we build volume meshes. So our terminology for the domain, or sorry, for the geometry at the base level is called a database. On top of the database, we create grid curves that contain a number of grid points in a certain distribution of grid points, and we call those grid curves connectors. Now, from connectors, we can create surface mesh entities that we call domains. And then from domains, a collection of domains, we can create blocks, which are volumetric grid entities. All right, so to get started talking about some new features, one of the biggest ones to go into Pointwise version 18 is called mixed cell domains, the ability to create mixed cell domains. Now, I should also mention that this webinar, we're going to be focusing on unstructured and hybrid meshing. We're not going to be focusing on anything structured, okay? So what you're seeing here, mixed cell domains, is going to apply to unstructured and hybrid meshing. You'll see that there's a domain there that consists of both quads and triangles. So now a domain doesn't have to consist purely of quads or purely of triangles. It can consist of a mixture of the two. And there are three algorithms that you can choose when you're creating unstructured domains. You can choose Delaunay, advancing front, and the new advancing front ortho technique. Not only that, but you can choose the cell type, whether they're all triangles or triangles and quads. What you're seeing on the screen is the new advancing front ortho algorithm and triangles and quads. It's a quad dominant surface meshing technique. In the growth portion of this domain, we use an algorithm that we call 2D T-Rex, stands for anisotropic triangle extrusion for the surface mesh, and we use this technique to resolve areas of high curvature anisotropically. So we can stretch elements, in this case kind of in the span-wise direction, while packing them normal to a particular boundary to resolve areas of high curvature using fewer elements than if we were to do, say, isotropic refinement. Well, with this technique now, you can also choose the cell type, whether that be all triangles, so right-angled triangles, or triangles and quads, and you'll get a quad-dominant nature in the growth portion of that domain. The next major feature is mixed cell blocks. So a mixed cell block is, as its name suggests, a block that consists of more than one element type. So before Pointwise version 18, a block could only consist of a single element type, whether that be all hexes, tets, or pyramids, or prisms. However, in Pointwise version 18, now a block can consist of all of those various element types. So what you're seeing here is a block that has hexes and prisms in the boundary layer, and then pyramids and tetrahedra in the far field. This was created using our 3D T-Rex algorithm. It's an advancing normal technique for creating these hybrid viscous unstructured grids. And I'll be talking a little bit about this more when we get to the demo portion of the webinar. The next major feature is shape creation. Now, you used to be able to do this via a script, and you could also do it, for example, to create a sphere by creating a curve and then revolving it to create that sphere. Well, now this utility is available directly within Pointwise. You can create primitive shapes. You can create polys, boxes, cylinders, cones, spheres very easily, interactively, picking a couple of points in the display window. You can move them around. You can rotate them. You can scale them, all very easily. I mean, creating primitive shapes is great for geometry purposes, but it's also great for creating things like, say, your far field boundary, and that's how we're going to use it today. You can also use shapes to create something that we call grid sources. Now, a grid source, unlike a baffle, which is how you would provide volumetric refinement in Pointwise before sources were introduced, with a baffle you're basically fixing points in the volume using a domain, for example. With a source, you're creating this object. It can cut through the geometry. It can cut through the boundaries of the mesh, and you're assigning a set of sizing attributes to that source, a spacing and a decay value, and these attributes and this source are going to influence the volume mesh and its size field. So here you see a couple of sources behind the wingtips of this aircraft, and you can see their influence on the volume mesh in the next slide. So here you can see that those two sources have influenced the volume mesh in their vicinity. And that's grid sources. So with that, those are the 4 features we're going to cover in depth for this sailplane case study. You can see some of the specifications over on the right. The one that I want you to take away is the surface grid spacing of 25 millimeters. We're going to use this surface grid spacing when we create the domains for the aircraft. This spacing represents kind of your baseline mesh for this case, maybe something like a coarse grid in your grid family, okay? And that's what we're going to, again, use to create the baseline surface mesh for the aircraft, and then we're going to do some additional refinement. So with that, I'm going to jump over to Pointwise, and we're going to start meshing right away. Now, like I said, if you have any questions at any point during this process, just type them into the questions box. I've already noticed that there are a few over there. We're going to get to those at the conclusion of the webinar. Like I said, Carolyn's going to jump on and start answering those at that time. And then if you can't get your questions answered, or you think of something after the webinar is over, we'll provide an email address where you can send those as well. Okay, so in the display window you see that I have an aircraft geometry. All right. The first thing I'm going to do is go to the defaults panel, and I'm going to set up some meshing defaults. This is the kind of the process I take when I create a mesh for really any geometry, not just an aircraft, but any geometry. I like to set up my defaults so that when I go ahead and create my grid entities, that they basically inherit these defaults, these attributes, so that I don't have to spend too much time modifying them downstream in the process. The first thing I'm going to do is change my connector average grid spacing to 25 millimeters. Now we're working in meters here, so 0.025 is 25 millimeters. That's going to be my average grid spacing, or my grid point spacing on my connectors. I'm not going to do any curvature-based refinement on the connector or domain level at this point, because that sort of refinement is isotropic in nature, meaning that to resolve areas of high curvature, like say the leading edge of the wing, I would have to pack points along the spanwise direction to refine that isotropically. I don't want to do that. I'm actually going to go ahead and use 2D T-Rex to do that in just a little bit, because I'd like to stretch those elements in the spanwise direction while preserving that curvature. So that's all I'm going to set for the connector defaults. I'm going to go to the unstructured domain and block frame, and I'm going to start at the isotropic frame for domains and change the algorithm to advancing front ortho and the cell type to triangle and quad. Again, that's our new algorithm, and triangles and quad means that we're going to get a quad dominant surface mesh. Next, I'm going to change my quad max included angle to 150 degrees. And what that's going to do is if Pointwise creates a quad element that has an included angle greater than 150 degrees, it's going to split that quad into two triangles. All right. So I've gone ahead and set that. And then the quad max warp angle, I'm going to leave that as 30 degrees. And we'll jump back to the slides and you can see how that warp angle is computed. So if you take a quad, now a quad is not planar. It's got 4 points. So if you take that quad and you diagonalize it two different ways, you'll get a set of normals, and you can take the angular deviation between these normals, and the warp angle is just the maximum angular deviation. And if it violates that value, if it's higher than that value, what we'll do is we'll split the quad into two planar triangles. And that's all the warp angle is. So typically you'll have high warp angles on curved surfaces if you're using kind of a coarse surface mesh to resolve those. The next attribute I'm going to set up as a default is my domain boundary decay. I'm going to set that to 0.85. That varies from 0 to 1. And what the boundary decay does is, when you build a domain, it's assembled and initialized using its bounding connectors. The number of points on those connectors, the distribution of points, kind of any clustering you have influences the initialization of that surface mesh, of that domain. So the boundary decay will take that information on those connectors, the clustering and everything, and propagate it further into the interior the higher that boundary decay value is. So I'll typically set that anywhere between 0.85 and 0.95 for my application. So I can take that information and propagate it further into the interior of the domain so I can get a nice smooth transition. That's all I'm going to set up for isotropic. Now I'm going to go to T-Rex. Again, T-Rex is going to be used to resolve areas of high curvature on the surface. And so we need to be able to specify an initial height, a number of layers, and a growth rate in order for it to do that. And then we would need to specify some boundary conditions, like which boundaries are we going to grow away from, etc. And we're going to do that a little bit later when we actually go ahead and apply 2D T-Rex. So right now what I'm doing is I'm just setting up the attributes for the solver so that I don't have to do this in the future. So 20 layers at a growth rate of 1.2. We're going to turn on push attributes, and I'm going to toggle on triangles and quads. All right, so we're done with T-Rex. Now let's go to the blocks. So volume mesh. We're going to go to the isotropic frame. I'm going to change my boundary decay here to 0.85 as well. That's all I'm going to change. And then we're going to go into the T-Rex frame, and this is how we're going to generate our viscous volume mesh. All right, so I want 50 layers at a growth rate of 1.2. I'm going to create all element types, tets, pyramids, prisms, and hexes. I'm going to increase my collision buffer to 2. And what the collision buffer is going to do is, as you're advancing off of the surface, if fronts are starting to collide with each other, the higher the collision buffer, the more space is going to be left in between those fronts. So they'll kind of stop a little bit sooner than they would otherwise for higher quality isotropic tetrahedra to be developed in that gap region. I typically almost always set this to a value of 2 or larger. Next is the skew criteria. I'm going to change the maximum angle skew criteria to 170 degrees. Now, just a note about T-Rex and skew criteria. T-Rex is an advancing normal technique. Unlike other kind of advancing layer techniques, you don't have to have the same number of layers around the entire aircraft. T-Rex is able to stop locally when any of these attributes or criteria are violated in the advancement of those elements, but continue advancing elsewhere where it's not violating. So if the collision buffer is being violated, if my maximum angle metric is being violated, it'll go ahead and just stop that point locally, but continue advancing everywhere else. You can get these nice thick layers of elements. Now, the only skew criteria I'm going to set in this case is the max angle. I'll typically set that anywhere from 165 to 175 degrees. And in this case, I'm going to set it to 170. I'm actually going to have a little bit longer discussion about why I'm setting it to 170 degrees in just a little bit. That's all I'm going to set for T-Rex. I'm going to set my wall spacing to 0.5 millimeter. So given the flight conditions of the aircraft, targeting a Y plus of anywhere between 50 to 60, I'm setting my wall spacing to 0.5 millimeter to do that. All right, so I'm done setting up my defaults. And like I said, the defaults are only going to be applied to the entities that I'm going to create. After the fact, I can still adjust any of those attributes, and I'm definitely going to do that as I start refining the surface mesh. So let's go ahead and pick the geometry. We'll make sure Unstructured is selected in the toolbar, and I'm going to go to Create on database entities and toggle on a connector join angle of 45 degrees and create my surface mesh. And what that's going to do is any connectors that are connected to each other that have a turning angle less than 45 degrees, it's going to join those, reducing the number of connectors in my mesh and the complexity, because ultimately I'm going to go ahead and start refining some connectors. So the fewer connectors I have to work with, the quicker I'll be able to go through and do that refinement. I'm already seeing some really great questions in that frame, so keep those coming. We definitely appreciate those. All right, so I'm going to turn off the view of the geometry, and let's just switch this to hidden line. Okay, so here's our kind of baseline isotropic surface mesh. As you can see, it's pretty much all quads, and in fact, if I go look at the cell count, you'll notice that there are only 447 triangles and over 26,000 quads. And again, this is unstructured quads, so we didn't have to create it like we would, say, a multi-block structured technique on the surface. We're creating unstructured quad surface meshes. However, obviously this is relatively isotropic, and I need to do some refinement. I mean, my arrow surfaces, such as my horizontal, that's pretty coarse there at the leading edge. Over here at the tip as well, that's pretty coarse, needs some refinement. There are some small features here as well that are going to need a little bit of refinement. But like I mentioned, again, those defaults, I set those up so I can get 90% of the way there with my surface mesh. Now I can just go ahead and start refining it. So I'm going to go and select some of these connectors. Okay. And I'm going to go to grid dimension and change their average spacing to 10 millimeters. We're going to shrink that just a little bit to refine those. And so what it's going to do is it's going to go ahead and figure out how many points it needs on each one of those connectors to achieve that target average grid spacing of 10 millimeters, and then it's going to go ahead and update those as well as the domains that utilize those connectors. So you can see it's gone ahead and updated that, and I have a little bit better refinement, and in effect I've reduced the warpage of those quads in doing that refinement. However, you'll notice that I've got this difference in cell sizes at these nodes. These points that you see, the ends of connectors, are called nodes, and what I'd like is for all the spacings at a node to be about the same, and that's going to reduce my area ratio, result in a much smoother mesh, and we can go ahead and do that pretty easily by just, if you're unfamiliar with Pointwise, you'll notice there are some arrows at the ends of all of these connectors. Those are called spacing constraints. Now for a given connector, it's going to have a number of points, and then you can cluster points towards either end, or you can even cluster them on the interior of a connector, and those points are distributed using some sort of distribution function, and by default that's hyperbolic tangent. We're actually going to go ahead and change that for a few of these connectors later on in this process. But for now, I'm just going to set up all the spacing so at nodes they're consistent. The easiest way to do that is just select one. Let's go ahead and copy that using Control-C, and then select the spacing constraints that you want to match that and paste it using Control-Shift-V. And it'll go ahead and pull all those points, redistribute the points along all of the connectors, and then update the surrounding domains. And you can see now all of the quads in that vicinity are the same size, and we have a nice smooth transition. So I'm going to go ahead and do that for a few places on the aircraft. So kind of down here at the base. Okay, and there's a few places up here as well. All right, so that's all I'm going to do for now. Pretty happy with that, and you can see that points have been, again, this connector has the same number of points, but now they've been clustered towards either end, so things have coarsened up on the interior a little bit. Again, we're going to go ahead and fix that in just a few minutes. But now what I want to do is I want to provide some additional clustering towards the ends of all of these arrow elements where I'm going to use 2D T-Rex to resolve curvature. And what I mean by that is I know the spacing I'm going to use to resolve that curvature. What I'd like to do is constrain the spacing at either end of these elements to have that same value so that I terminate at isotropy at the end. And you're going to see exactly what that does for the mesh. So we're going to go around and select all of those spacing constraints and the main wing as well, and out there at the tip. And I'm going to change those to 2.5 millimeters. And it'll go ahead and update all of those distributions as well. And then I'm going to go ahead and clean up a few more spacings, and then we'll talk about how in the world I came up with 2.5 millimeters. All right. So yeah, that looks pretty coarse now, right? Don't worry, we will fix it. All right, so I'm going to go ahead and set up some spacings, kind of tighten things up a little bit. All right, so we've got that. Copy, paste it to those two. I'm going to copy that spacing, and we're going to paste it there. All right, so I'm pretty happy with that now. Everything is set up the way that I want it. All right, so how did I come up with, and don't worry about this, we're going to fix it. I know it doesn't look pretty right now. We're going to go ahead and fix that pretty quickly. But how did I come up with 2.5 millimeters? Well, let's jump back to the slides. I came up with that based on the turning angle. So if you go to pointwise.github.com, you can download this turning angle calculator, which allows you to compute the turning angle at a grid point. And so for the case of 2.5 millimeters, that's a pretty good spacing to use for all of those arrow elements, at least initially, to get turning angles, anywhere from say 5 to maybe 20 degrees. Again, this is going to represent kind of the coarse mesh in our grid family, so you can go ahead and refine that as you see fit. But you can use this turning angle calculator to kind of get an idea as to what that spacing should be to achieve the turning angle that you want for those particular entities. All right, so the next step is applying 2D T-Rex to the arrow elements to resolve curvature. And to do that, I'm going to go ahead and select all of those domains and go into Grid T-Rex. Again, all of my attributes have already been set up. I don't need to worry about that. All I need to do is set my boundary conditions. So I'm going to create a new boundary condition. I'll call it leading edge and trailing edge. It's going to be of type wall. And I'm going to change that spacing again to 2.5 millimeters. And I'm going to grab all of the boundaries that I want to grow those elements away from and drop them into that boundary condition. Again, those are going to be the boundaries where I'm going to grow these high aspect ratio elements away from to resolve curvature, so that way we're not doing isotropic refinement. The next thing I'll do is select my match connectors, and I'll talk about that as well. So I'll go ahead and select those, and we're going to drop those into that boundary condition. Okay, and the match connector, oops, let's go ahead and undo that step. I dropped them into the incorrect boundary condition. So we're going to go leading edge, trailing edge. We're going to do wall type again, 2.5 millimeters. We'll select all of those boundaries, put those in that boundary condition, and then we're going to create a new boundary condition. We'll call this one root and tip. And that's going to be a match type boundary condition, and that's where we're going to drop those. So let's go ahead and do that again so you can see it twice. All right, so now we'll put those in that boundary condition, okay? And what the match condition is going to do, coupled with push attributes in the T-Rex frame, is that it's going to take the attributes of that growth on the surface and it's going to apply them to that connector, meaning that initial spacing, that growth rate, that number of layers. It's going to go ahead and update the distribution of points on that connector so that they're matching. So I have a really nice transition and good distribution of points, not only on that connector, but immediately adjacent to that connector in the domain. All right, so that's what those match connectors are going to go ahead and do. So with that, we can go ahead and initialize those domains. And once they're initialized, you'll be able to see why I went ahead and clustered points towards the ends of those connectors. All right, so why did I go ahead and cluster points towards the ends of these connectors? Well, I did that so that all of the cells in this vicinity have the same size. If I didn't do that, I would have some anisotropic stretching in the spanwise direction directly adjacent to kind of these smaller quads, increasing my area ratio. And here we come back to talking about area ratio, and we're actually going to go examine that once we're done with the surface mesh. But the idea is if you keep your area ratios low, when you generate that volume mesh, you're going to have a really high quality volume mesh in these vicinities. And that's because low area ratios means that the cell sizes are all roughly equivalent to each other in kind of their local vicinity. So smaller elements on the surface, when you advance those into the volume, are actually going to stop sooner. They're going to reach an isotropic or uniform state sooner than larger elements. So you can see that if you had large area ratios, you'd have a small element directly next to, say, a large element. Well, that small element, as it advances, will stop sooner in fewer layers than that large element. And that could actually influence the growth of that larger element. So keeping things about the same size, especially at nodes like this, is really going to improve the quality of the resulting volume mesh, because in the end, everything is going to come off of the surface. So you need to really ensure that you have a high quality surface mesh. And that's why I went and clustered points towards either end using that same 25 millimeter spacing. But you can see what 2D T-Rex does. I have stretching in the spanwise direction. I'm packing normal. I'm packing in the chordwise direction to resolve that high curvature. All right. Okay, so now that we've done that, you can see that a few of these match connectors got a little bit overly refined. The interior of some of these connectors now, because I clustered points towards either end, it's pretty coarse, right? We're not, achieving that 25 millimeter resolution that I really wanted to achieve on the surface, and you can see that front kind of breaks down into this, unstructured quad sort of front kind of in the interior here. And I'd like to go ahead and fix all of that. And the way to do it is by adjusting the distribution of points on those given connectors. So again, we specified spacings at either end, had a fixed number of points. Those points are now distributed along that curve using some distribution function, in this case hyperbolic tangent. So we can go ahead and update that, okay? So to talk about that, let's go ahead and pull up a little schematic of a growth type distribution. So here we have a connector with some points on it. At either end we have a growth region, and in the interior we have a uniform region. So my goal is to have a 25 millimeter spacing on the interior. That's this DS2. That's what I want on the interior. I know what my initial spacing is at either end. I know what my growth rate, what the growth rate I want to be is 1.2, because that gives me a nice smooth transition of points along that connector. So if I know my initial spacing, and I know my growth rate, and I know what target spacing I want on the interior, the only variable left is the number of layers. So using this equation, I can compute how many layers I need to use from either end to achieve that target spacing on the interior. So let's go ahead and use that to update this connector. So I'm going to select that connector and go Grid Distribute. I'm going to go to the Functions tab. I'm just going to change it to type growth. I've already plugged the numbers into the equation. That's 13 layers at a growth rate of 1.2. So we're going to do that from either end. We're going to set an optimal dimension, click OK, and then it'll go ahead and update that. And that's much better. That's kind of what I want. However, I need to do that for a number of connectors, and I don't want to do that manually, one connector at a time. I'm going to go ahead and undo that. Those of you who know me know that my solution to problems like that always come down to scripting. So if you go to pointwise.github.com, you can download the Con Geometric Auto Dimensions script. With this script, when you launch it, a user interface will pop up. You'll pick a connector. You specify the begin and end spacing, an interior spacing, and your growth rate. It'll go ahead and run, and it'll automatically update that connector for you. For this webinar, I took this one step further. I stripped out the user interface. So now I plug those numbers into the script directly using a text editor. Typically, those don't change too much from project to project. And then I can select any number of connectors and just run that script. So that's what I'm going to go ahead and do. I'm going to select all of those connectors that I want to update, including the connectors that got a little bit overly refined. So you can see the tips ended up looking okay. And I'm going to zoom in to the tail here, and we're going to run that script. Again, great questions. I'm seeing some of these, and I'm actually going to be answering a few of these questions in this webinar. So definitely stay in, and you'll see the answers to some of those questions. I see one about area ratio, and I saw one about quads versus tris and that sort of thing, and those are coming. Answers to those questions are coming up. All right, so it's going around all of those connectors I selected and changing their distribution function to growth, updating, calculating how many number of layers they need, and here is the result. And you can tell I really, really love scripting, and the result that I'm seeing here is absolutely fantastic. Just for dramatic effect, let's just undo that and let's redo that. You can see we went from here to here. This surface mesh, and I'll give you a tip. If you're using quad dominant technique, you're going to get your best results by keeping that domain as uniform or isotropic as possible. Does that mean you can't do any sort of refinement? No, absolutely not, because I'm doing refinement at the leading edges of these surfaces. I'm doing refinement at the ends of those connectors as well. The only reason it looks as uniform as it does is because I changed the distribution and the number of points on those connectors. It's a much smoother transition from the clustering at the ends using that growth rate of 1.2 and targeting that 25 millimeter resolution on the interior and just updating everything for me automatically. And again, I'm very happy with this result, and I think you will be too if you use a technique like this when you're using the quad dominant surface meshing algorithm. All right, so with that, I'm going to go ahead. There are a few triangles left in this guy. I'm just going to go ahead and reinitialize the fuselage domain. See if we can wipe some of those out using the new boundaries. Okay. All right, so I'm pretty happy with the surface mesh of this aircraft. I have the refinement I need on my leading edges. If I zoom in here, you can see that, again, I've kind of clustered points towards this corner to terminate those layers immediately. So you'll notice there's 1 layer, 2, 3, 4, 5, 6, 7, and all along, and this nice 45-degree line coming out of that corner. That's what I look for when I'm using 2D T-Rex, because what that tells me is that I've clustered points towards the ends, towards the root and the tip appropriately, and now all of my cells in that vicinity are roughly the same size. All right, so I look for that nice 45 coming out of that corner. All right, so I have my surface mesh. The next step is examining the quality of that surface mesh. I'm going to hammer this hard because I think this is important to talk about. There's no reason to take a surface mesh that hasn't been examined and try to generate a volume mesh from it, okay? Because in the end, like I mentioned before, you're going to be advancing elements off of the surface. So if you haven't looked at the quality of the surface, or the quality isn't, up to what you want it to be, right? It's violating some metric that you've specified. Go ahead and inexpensively make modifications to the surface rather than generate a volume mesh to identify those problems later and expensively have to fix them, okay? Because generating a volume mesh, granted, I mean, it is an expensive process. It's much more expensive in terms of time than generating a surface mesh, okay? So I'm going to go ahead and select all of my domains and go to examine, and we're going to look at area ratio. Area ratio is a big one for me. You've probably heard me talk about it a lot in the past if you've seen some of my other videos. In this case, my area ratio is 10.45, okay? And I'm going to go ahead and toggle on the histogram and set my max to 8. And you can see there are 6 cells that have an area ratio above 8. Okay, let's go ahead and try and find those. So we'll turn that off. You can see there's one here at the tip, and we would expect that. There's a small triangle directly adjacent to some larger triangles. And let's see here, it looks like down here at the base there are some as well as some up here at the top. And I actually need to update that connector. And if I do that, let's go ahead and update this connector. So this has 27 points. Let's give this guy 27 points. And let's go to grid distribute and just copy the distribution from this connector. And we've fixed that. So that's what I'm saying is right now, I mean, just in that 30 seconds of looking at the area ratio, I was able to identify an area where I needed to update the dimension and distribution of grid points to resolve that problem. I'm happy to have found that problem now than later when I'm generating a volume mesh. Okay, so let's go ahead and grab all of those domains again and examine the area ratio. And now we only have 4 above 8 with that max of 10.45. Okay, so at this point you're probably saying, well, Travis, in the past you've mentioned a maximum of 3 to 4 for area ratio, and you're absolutely correct. If you're generating a surface mesh that consists solely of triangles, your maximum should not exceed, say, 3 to 4. Okay, because you can control that pretty easily. What we've found is when using quad dominant surface meshing, you can increase that max to around 8 to 10 and still generate a high quality volume mesh. And the reason is, these fronts tend to break down into quads. So right now we have this quad because of topology, right? We have this quad directly adjacent to this triangle, and that's how you're going to get a little bit higher area ratios when you're using the quad dominant technique, because you're mixing quads and triangles, and a large quad directly adjacent to a smaller triangle is just going to naturally increase that area ratio. Okay, but in our testing, an area ratio no greater than 8 to 10 when you're doing a quad dominant surface meshing is fine. But if you're doing pure tri, you should try to keep that between 3 and 4. All right. So in this case, I'm pretty happy with the surface mesh. I know where the high area ratios are, so that way when I generate the volume mesh, I can keep an eye on those locations to see if they really do cause a problem. But again, they should be fine in this particular case. All right, what's the other metric I should look at? Let's look at maximum included angle. In this case, my max is 147. You should try to keep your maximum included angle less than 150. That's one of the reasons why I set my maximum included angle for a quad to be 150 degrees, because if it violates that, it'll split it into 2 triangles. So what are some cases where you might exceed 150 degrees? Well, if you have geometry that basically just the topology of the geometry means that the mesh that you create on that surface is going to have an included angle greater than 150 degrees, that's one area. So there's a couple of ways to fix that, or a few ways to fix that actually. One, you can just refine. You could change the topology. I would suggest changing the topology of the mesh. You can kind of change up where the boundaries are, or you can just clip the geometry there and resolve that problem. But you should try to shoot for less than 150 degree max included angle for the quads and triangles that you generate on the surface. Okay, so now that I know my surface mesh is of high quality, I can start thinking about generating my volume mesh. I'm going to go ahead and copy and paste this. I'm just going to build out the full aircraft here. Okay, so there I'm building the full aircraft. And the next thing I need to do is build an outer boundary. I need to build my far field. Okay, so to do that, I'm going to use the new shape creation tool. I'm going to go to create, draw shapes, and we're going to create a sphere. I'm going to turn on the geometry, and for a sphere you just need to pick 2 points. I'm going to pick a point that I know is on the symmetry, which is right here at the back of the tail, and we're going to look in the negative x direction, and I'm going to pick a second point. And I've basically defined my sphere. So no more creating a curve and doing a revolve. You can just go ahead and quickly draw a sphere. And I'm going to hit the T key to get into the translate mode. I'm just going to center it right here on the aircraft, and then I'll hit the D key to get back into draw mode. So you can see there are several modes. You can translate, rotate, and scale about either the local coordinates of the object you're creating or the global coordinates of your grid system. In this case, I just translated it over in the Z direction, kind of centered on the aircraft. If I were doing half an aircraft, I could specify half by just clicking the half button, and now you can see I have half a sphere here. I'll go ahead and click full. And for this case, I need to increase the radius. So one rule of thumb for this is if you're doing an aircraft like this, your radius of your far field sphere should be at least 20 body lengths away. So I'm going to go ahead and increase my radius to 130 meters for this case. So I have a nice outer boundary for my case. So I'll click OK. And the next thing I'm going to do is set up some new meshing defaults. My average grid spacing is going to be 13 meters. That's 2 times the body length of the aircraft. And then for unstructured domains and blocks, I'm not going to create a quad dominant mesh out there. I'm going to go ahead and create an advancing front tri-surface mesh. And the reason for that is there is no reason to have quads out there in the far field. And the reason for that is we're going to have tets out there, okay, tetrahedra. And if you have quads, to transition to the triangular faces of the isotropic tets is going to require a pyramid. And so I'd have like a bunch of pyramid, like a layer of pyramids over all of those quads out there in the far field. There's no reason for that. Just leave it as tri to match up perfectly with the isotropic tets that are out there. Okay, so that's why I've gone ahead and done that. And I'm just going to hide the grid lines of that outer boundary so I can see the aircraft. And we'll turn off the geometry here. Okay, so I've got my outer boundary, I've got my aircraft, which represents the inner boundary. Now let's go ahead and build that block. So I'm going to go to create, assemble special block. I'm going to go to the automatic tab, turn on create baffle faces, just select everything and say assemble. Now what this means is, what baffle faces mean is that an unstructured block can consist of multiple faces. Baffle faces is going to be an interior face, in this case the aircraft. So you'll see that I have in the table 2 closed faces. That's the outer face, the sphere, and the inner interface, the aircraft. The interface, the aircraft. And then one block is created. And if you look, you can see the normals are pointing inward for the sphere. And if I zoom into the aircraft, they're pointing outward from the aircraft. And that basically means we're going to be meshing in between the two. All right, so that's the definition of our block. We'll click OK to accept that. So now what I have is an empty block, all right? And the reason it's empty, right now this is a watertight representation of our volumetric computational domain, and it's empty because the process of initializing a hybrid viscous block, again, can be computationally expensive. So we don't do that without you telling us how you would like us to do that, without setting up some set of attributes beforehand. So right now it's just empty. So here's the really cool thing about that is, yes, it's empty. There are a few more steps we can take before we even create the volume mesh, before we even initialize it, populate it with elements, to kind of guarantee that we're getting the distribution of points within that volume that we want. So with that block selected, I'm going to go and take a look at the size field. This is a new examine metric, requires no points, no cells. You can do this with an empty block. I'm going to go ahead and let's just take a Y cut. I'm going to kind of cut right through the wing of the aircraft. Let's drop this down a little bit. And let's go take a look in the negative Y direction. And we can see the aircraft. Let's minimize this a little bit to bring that closer. What you're seeing now is the approximated size field of the elements that are going to be generated in the block before they've even been generated. This is a huge time saver. Why? Because just looking at this, I get an idea of how quickly those elements are going to grow from the surface into the far field. And I get a number associated with that as well. If you look over here in the histogram or you look down here at the bottom, you can see as I hover over this, you're seeing the approximate grid size. Okay? So if I zoom in here just behind the wing, we've got about 12 millimeter resolution. We move away about 20 millimeters, 30, 50, as we move away from the aircraft, right, out to here where we've got half a meter resolution, etc. Okay, so looking at this, one of the things that I want to do is I want to track the tip vortices. I want some additional refinement behind each of those wingtips because those cells grow pretty quickly. It's going to diffuse that solution. I want to add some additional refinement. All right, so I'm going to go ahead and close out of this, and I'm going to create another shape. In this case, we're going to create a cylindrical shape. I'm going to change the entity type to source, and let's go ahead and pick that point. And we're going to look in the positive Z direction. Zoom in here. I'm going to pick a second point. I'm going to rotate this around, and I'm just going to sketch out a cylinder. It can cut through the geometry, that's fine. I'm going to unlock the top and kind of flare out the end here a little bit. Kind of pull that downstream. This is all parametric, so you could have a script that changes the parameters of this source, run different calculations and see how that influences the solution. So with that, I'm pretty happy. I'm going to go ahead and click OK. And now I've got this source. Again, the purpose of a source, it can cut through boundaries, it can cut through the geometry. The purpose of the source is to provide volumetric grid refinement in the isotropic portion. It's not going to touch the surface mesh, it's not going to touch the boundary layer mesh, it's not going to destroy any topology or anything like that. It's just going to influence the isotropic portion of the volume mesh outside the growth region that you've specified. So I need to be able to specify some sort of cell size for this entity. So I have it selected. I'm going to go to Grid Sources, and in here is how I can specify the cell size for the source. I can do it either interactively, so I can kind of grab this handle, and the diameter of that circle is equivalent to the cell size. But in this case, I saw, looking at the size field, I want a 20 millimeter resolution, and I want to propagate that downstream. I'm going to increase my decay to 0.85 to keep in line with my boundary decay for both the surface and the volume. And you'll notice at the other end that sizing is a little bit larger, so it's linearly interpolating from this size to this size for the length of the source, but what I'd like is just a constant source. I'm talking 20 millimeter resolution throughout the entire cylindrical source that I've created here. Okay, so I'm happy with that. I'm going to go ahead and click OK. And if I want to change any of those attributes, I can do it right here in the list panel. I can just double click and type in a new value. I can add a couple of entry boxes to my toolbar as well to change that size or that spacing and decay. And I have one more opportunity in the grid solver, which you'll see as well. So with that selected, I'm going to go ahead and copy and paste and mirror that so I get one on the other side. And let's go ahead and examine the size field again. We're going to take that same cut, and now you can see the influence of those sources on the size of the cells in the volume mesh. Again, no volume mesh has been created yet, but now we're seeing the effect of those sources that we've created. So you can kind of use this, you can iterate at this stage to get the distribution that you want in the volume before you go ahead and actually initialize the volume. So this technique coupled with looking at grid quality on the surface mesh is really going to reduce the number of iterations you may need to perform on the volume mesh level. Okay? Because again, when you initialize that volume mesh, it's going to take a little bit of time. So you want to reduce the number of times that you're doing that, and you can use these two techniques to significantly reduce the amount of time that you're spending on the volume meshing portion of the process. All right, so I'm happy with that. Okay? So the next thing we need to do is build our volume mesh. However, one of the things that I wanted to talk about was, you may be watching this, I've already seen a question very similar to this come up, is, Travis, why in the world would I ever use triangles again? If the quads look like this and I'm going to get hexes in the volume, why would I ever use triangles on the surface again? That's a very, very good question, and there's an answer to that, okay? And it comes down to the way T-Rex is going to be advancing elements off of the surface. So T-Rex is anisotropic tetrahedral extrusion. It's a tet meshing algorithm that advances right-angle tets off of the surface, and then after the fact it combines them. And it does that because you get more flexibility, it's more robust, all the faces are triangular, And then in the end, it'll go ahead and combine all of those into hexes and prisms, pyramids, and then have tets in the far field, okay? The thing is when you give it a quad mesh, all right, we need to somehow expose triangles. So let's go ahead and open up the presentation again. The way you would expose triangles from a quad is you need pyramids, all right? So here's a base pyramid that would sit on top of a quad, and here are 4 surrounding pyramids that expose 4 triangular faces. Now all of these elements together can be combined into a single hex after the fact, okay? But this topology exposes 4 triangular faces. Here's where the problem can come in. That angle right there can get kind of large if you have any sort of stretching on the surface, such as this. So here's a higher aspect ratio quad. There's some stretching in this quad. We're looking at the same angle, theta, and you can see how it can get pretty large, and it's going to get larger the higher that aspect ratio. Well, again, you're going to be creating tetrahedra right off of that, and if you have your skewness criteria set, like in my case, I set the max angle to 170 degrees. If that angle right there exceeds 170 degrees, that element is going to stop, and you'll see something like this. All of those elements are stopping at the leading edge. All of those elements are stopping at the trailing edge, and that's because, again, that aspect ratio that you use for the surface element doesn't necessarily support the maximum angle skew criteria you have specified, and vice versa. All right? So here's a table kind of showing you aspect ratio versus interior angle theta above. So for my case, going back to the beginning, 25 millimeter surface resolution, 2.5 millimeter resolution at the leading and trailing edges to resolve curvature should give me an aspect ratio of around 10, give or take, you know, because if it's not 25 millimeters exactly. In fact, if we go back and we take a look at one of these domains and examine the aspect ratio, the maximum is 9. It's happening here at the leading edge and the trailing edge. So I have close to an aspect ratio of 10, okay? That means that that angle would be 168 degrees. Now I'm using 170 degree skew criteria, max angle skew criteria for T-Rex, which is larger than that value, so I'll be fine. However, it's not uncommon for myself and others to use much higher aspect ratios on the surface. So, I mean, for most aircraft, I'm using aspect ratios on the order of 20 or 40. If I were to use 40, that angle theta above would be 177 degrees, which would be much larger than the 170 degree limit that I have set. Okay, so it would stop. So how do you get past that? Well, you use triangles. Okay, if you diagonalize a quad, now that right angle becomes the largest angle. Okay. And the easiest way to go about doing that is if you've created a quad dominant surface mesh, you can diagonalize it. Okay, it's pretty easy to diagonalize that domain. But if you know, I would say, if you know you're going to be using higher aspect ratios for your meshes, go ahead and you can choose any of the algorithms, but choose the triangle cell type. All right, and I'm going to show you a little trick in T-Rex where you can actually recover quads after running the algorithm. So what you're seeing here is the new advancing front ortho algorithm, but I'm using triangles instead. And again, the reason I'm using triangles is T-Rex is going to be advancing right angle triangles or right angle tets off of the surface, and they're not going to violate that angle because that interior angle now is much smaller. And then after the fact, it's going to combine elements. Well, how is it going to do that? Let's go ahead and select this block and go to Grid T-Rex. It's all about this frame right here, this cell types frame in T-Rex. So right now it's set to all. That's tets, pyramids, prisms, and hexes, meaning it's going to take your mesh as is, bring it into T-Rex, and advance right off that surface. You're going to get hexes on top of quads, you're going to get prisms on top of triangles, and again, to transition from quads, it's going to have to use pyramids, and then after the fact, you would get your hexes. Well, if you brought a tri-surface mesh in here, and you use this third option, this all and convert wall domains, what it's going to do is it's going to identify the triangles on the surface that can be combined into a high quality quad, and then it's going to do the advancement. So it'll advance off of the triangles as they are, but it already knows which elements on the surface can be combined into quads. When you get the prisms in the boundary layer, it knows which two prisms can be combined into hexes on top of the two triangles on the surface that can be combined into quads. And in the end, you're going to get a quad dominant surface mesh with hexes in the boundary layer region. Okay. This was kind of a long discussion, but I know that we would get that question is why would I still want to use triangles? And the answer is if you're still using high aspect ratio elements on the surface or you need to for your application, go ahead and use triangles, but you can still recover quads on the surface using this third radio button here. Now for my case, I've kept the area, or the aspect ratio I should say, I've kept the aspect ratio down. And it does support the skew criteria that I have specified. So in this case, I'm going to be just fine, and I'm going to go ahead and extrude off of this surface directly. So all of my attributes here are set: layers, growth rate, collision buffer, max angle, everything here is set. I'm going to go to the boundary conditions frame, and the only boundary condition I really need to set is for the aircraft. I'm going to put it in a new boundary condition called aircraft, and it's going to be of type wall. Automatically picks up that 0.5 millimeter resolution that I want in the boundary layer, and then we would go to solve and click initialize. And actually before I do that, I should mention, I told you I would show you this before, in the attributes frame you get one more opportunity to adjust your sources. So in the sources frame you can change spacings and decays, you can change the type from constant to parametric, etc. You can even ignore the sources, you can turn them off, you can turn off one or the other, that sort of thing, and then when you're happy with that you can go ahead and click initialize. So we're giving you multiple options to go ahead and adjust your sources. Okay, so you would go ahead and initialize, and that initialization takes about 8 minutes. So I've recorded the video and kind of sped it up so you can see that process, because there are a few things I wanted to point out. One, here we're advancing, we're already at layer 9. You can see a couple of points are stopping. And that could either be because we've those two fronts have started colliding, which is probably the case. These are some concave corners. The other case could be that those elements on the surface are much smaller than some of the larger elements, so they could be reaching isotropy already. Okay, so we're kind of keeping an eye on that. There's a few other points stopping. Again, I believe this is because those elements are, again, smaller, so they're reaching isotropy, and that's to be expected. And in fact, the entire front is eventually going to turn red because all of those elements have reached isotropy. Other stopping criteria are going to be, again, if it violates your skewness metrics, if you have a negative volume, if it reaches the maximum number of layers that you've specified. Those are all reasons for that front to stop. So now you're starting to see the entire front turn red, which we would expect as it's reached kind of a natural stopping point. All right, so here is the initialized volume. Let's go ahead and examine that. So we're going to examine the maximum included angle. In this case, the max is less than 174. If we toggle on the histogram, we can see a good distribution of interior angle quality. We can go ahead and take a cut through this. And yes, this is a very high quality volume mesh. You can zoom in here. You can start to see those elements in the boundary layer. And in fact, I can go ahead and change the function to cell type. And let's just brighten up the hexes here a little bit. You can see the hex elements in the boundary layer, their transition to the tet elements in the far field. Okay. All right, so with that, I'd like to conclude the demo and technical portion of the webinar. I just want to thank all of you for attending, and I did want to mention a couple of things. One, a recording will be available on our website by December 16th. You can get to that at pointwise.com/webinar. And what I'm going to do is I'm actually going to make the geometry available, the same geometry that I used for the demo, because you can take the video and that geometry and you can go through the process of creating this mesh as well. And obviously any questions you have, you can type them into the questions box now and we'll get to them. I notice again there are quite a few questions here, some of which we've already answered through the webinar. But if you have any additional questions after the webinar, or you start working on this, you download the geometry in the video and you start working through this, if you have any questions, you can email me at letstalk@pointwise.com and I'd be happy to answer them. So again, thank you all very much. We're going to open it up for Q&A. Carolyn is here, and so Carolyn, you can go ahead and come on and start answering some questions.
All right, Thanks, Travis. Appreciate all that. As he said, we've gotten a lot of great questions during the webinar, so I'm just going to start at the beginning and work my way through, and I may be reiterating things that Travis has already said, but I don't think there's a problem with that. So let's start off with the first question. Do the mixed unstructured blocks use more memory to initialize as compared to version 17? This is a good question. We did some pretty extensive testing moving from version 17 to version 18 because we did update our unstructured capabilities so extensively. I would say that there is a slight increase in memory usage between the two versions because of the additional capabilities, but it was not significant enough to cause any issues that we saw. Certainly, if any of you use the mixed unstructured blocks and you have a problem like an outlier where something takes a much longer time than you expected, please contact us at support@pointwise.com and we'll work on that individual case with you to rectify the problem. Our next question is about Fun3D. I use Fun3D, which expects triangular unstructured. Can you diagonalize the square mixed cells to make it all triangles like you can for a structured grid? Yes, you can. Travis showed you one way to diagonalize the cells, which was to use the Grid Solve Attributes panel with your quad dominant domains and simply select triangles, then initialize, and that would give you a triangular mesh but with the same vertex locations you had with your advancing front ortho mesh. There is a second way that you can also diagonalize a quad dominant mesh. That would be to select the mixed cell surface mesh and go to Create Diagonalize. That will diagonalize just the quad cells within the domain for you. All right, our third question is about sources. Will grid sources affect the domains and connectors that they encompass? If so, is it better to initialize the domains and connectors after setting up a grid source? This is also a very pertinent question and good. Right now, grid sources are just going to affect volume cells. We realize how desirable it could be to have them also affect the connectors and domains they encompass, but that part of the feature is not really quite there yet. We certainly hope to do so in a future version. If this is something that you're very interested in, please email us at support@pointwise.com and we will make sure we add you to that feature request so that you get notified when we have that capability. All right, this is a little bit longer question, so I'm going to read through it. I have an unstructured triangular mesh advancing front over complex geometry. If I'm creating a quad dominant mesh over the same domain, the number of cells reduces considerably. My first question is, how would the solution accuracy compare for the same setting in the case of a tri versus quad dominant mesh? I'm going to go ahead and answer question number one, which is from what we have heard back from our customers and from some of our own limited testing in-house, the solution accuracy and convergence behavior should improve with both node-centered and cell-centered solvers. Right now, off the top of my head, I don't know that this has been out long enough that anybody has a paper showing those results. This is all what we have heard word of mouth from our customer base. But it should improve. And some of that does have to do with the fact that the volume cells you get with a quad dominant mesh are more flow aligned than with a normal triangular mesh, and that can alone result in some of the improvements in convergence and accuracy. Question two, what about the medial dual scheme solver like SU2? With a quad mesh, the number of vertices will remain similar in number, but faces for a dual mesh will reduce in number. Again, this saves computation. What are the guidelines of using a quad dominant mesh from an existing tri mesh so as to save computational costs while keeping in mind solution accuracy? I feel like Travis covered this a good bit when he went over the comparison of using a triangular surface mesh and growing tets or prisms off of it versus creating a quad dominant mesh and growing it directly, or having Pointwise push quads down to the surface. But this also ties into my answer for the first question, which is you should see improvements in accuracy and convergence from your solver from moving to a quad dominant and essentially not quite a hex dominant volume mesh, or at least hex is in the boundary layer. So there's definitely a benefit to go ahead and moving to it. You just need to be sensitive to what settings you use to create that in Pointwise. Like he said, maybe starting from a triangular mesh and pushing down. And also, you need to be sensitive to the surface mesh quality so you get the best quality hexes generated off of it and the most layers. Thank you for that question. All right, our next question is, I'm a beginner in Pointwise. Any suggestions for getting started? This is sort of an open-ended question. I could probably talk about this for a long time, but I'm going to keep it sort of basic. A great first step if you're a beginner in Pointwise and you haven't done this already is to go to Help and Tutorial Workbook and start working through those tutorials from start to finish. We cover a lot of commonly used commands and features in the tutorials and a lot of different scenarios, and I feel those oftentimes get people off to a really good start. The second way to help get started with Pointwise, if you can, is to attend one of our in-house training classes. They're 3 days, and they usually help people really hit the ground running. We try to cover Pointwise from A to Z. And then the third technique I would use is we have an extensive selection of videos and past webinars and Let's Talk Meshing seminars on our website that you are welcome to look through. They cover a lot of topics. There's a lot of examples there, and these are invaluable to getting started with the software. And then finally, you can always email us at support@pointwise.com if you have a specific question. Okay, our next question is about boundary decay. Can the boundary decay be set to 1? I recently tried to use it, but it could only go to 0.99. I used to be able to set it to 1. This is a good question from the standpoint of I remember also doing this, setting it to 1. I do know there were some updates to our solver, just rectifying the GUI and making sure that it was clamping attributes to the appropriate limits. That being said, I don't know that this was one of the dialogues that was affected by those changes, and I'd like to look into this a little bit more to see if there could be a minor GUI bug there that's not letting you go to 1. So we'll need to investigate that a little bit further. So if you want to contact us offline, we'll log a ticket for that investigation and get back with you. All right, can you delay the regeneration of the surface mesh so you don't have to wait every time you change a spacing constraint? Okay, so this is a great question in terms of productivity, and I have experienced the same thing, and there's a good approach to use in this situation. So as you probably know, there are 2 ways you can change a spacing constraint. You can select it in the GUI and then go to the toolbar and type in the spacing constraint there and change it. And what will happen is, using the toolbar command, which is the quick and dirty way to do it, when you change that spacing constraint, it will change the grid points locally, and then the domain that's connected to that grid curve will also have to get updated, and that's where a little bit of time is involved. If that spacing constraint is actually used by multiple domains, then you have to wait for each of those domains to also get an update, and that can increase the amount of time you have to wait. Or if you have to update many spacing constraints, each time one of those gets changed, it forces an update of the associated domains. What I would recommend doing is, if you're just changing one spacing constraint, sure, use the toolbar, 1 or 2. If you know, let's say for instance with this glider, you're going to go around the wing and change quite a few spacing constraints, I would typically go into the grid distribute command instead. It's more of a modal command, and what happens is when you enter grid distribute, it's almost like you enter a bit of a sandbox, I guess you could say. So if I go in there and I select 10 different spacing constraints around the perimeter of a domain, and I change them and then apply that, I will have one domain update for the 10 spacing changes. If I contrast that to doing the same thing with the toolbar version, I would have gotten a different, I would have gotten 10 different domain updates for each one of those spacing constraint updates. So it helps to go into a mode, make all the changes that you want to make, and then apply them. That can save you considerable time. So if you're going to change many spacing constraints, use grid distribute instead to perform that function. If you just want to do one or two, just one-off spacing constraint changes, use the toolbar. All right, let's move on to the next question. What is the guideline of area ratio for a surface mesh for good extrusion in the case of a quad dominant mesh? Here at some places the triangle will be there next to a quad, which could lead to a high area ratio. In a triangular mesh, we keep area ratio under 4. I agree with you completely here. My recommendations for a triangular mesh is typically to keep the area ratio under 4 if possible. My recommendation for quad dominant meshes, because you can have a triangle next to a quad, is to typically keep that area ratio under 8. And Travis reiterated that and showed you this as well in his example. All right, we have a question about the location of the Pointwise scripts that Travis referred to in the webinar. So if you are interested in seeing any of those scripts, you can go to the web address pointwise.github.com. And that address was printed on one of the slides in the webinar, so when the recording goes live on December 16th, you should also be able to see it there. All right, will quads cause issues in an unstructured flow solver? All right, I think I addressed this already with my previous answer about the difference between using a triangular or prism mesh versus a quad dominant and hex mesh in flow solvers. In general, you should see convergence and accuracy improvements by moving to a quad dominant mesh with hexahedral on top. If you don't, I'd be really interested to hear about it. All right, our next question is about cell size. So keeping the cell size so uniform in size all over the surface is unrealistic for a large complex geometry vehicle. How can you increase the cell size in the areas far from the boundaries to reduce the number of surface cells and maintain good grid quality? So this is a multifold answer I'm going to give you. So Travis covered a good bit of this towards the end of the webinar when he started talking about area ratio and how area ratio and quality is dependent on the type of element you're growing off of. So you can take advantage of cell stretching and use that in your surface grids to save on cell count. There's just limitations to it, and the limitations are dependent on what your solver can handle. I have worked with people whose solvers were very sensitive and couldn't really handle cells that went over 160 for a max included angle, but I've also worked with people whose solvers could easily handle a cell whose maximum included angle was 179. So you do need to be aware of your solver's limitations and what types of maximum included angles they can handle. Once you know that, you'll know how much stretching you can employ in your surface mesh. In other words, how high you can get your aspect ratio for those surface cells to save on cell count. Travis was referring to how he typically uses an aspect ratio of around 40. In that example he used an aspect ratio of around 10. I've recently had meshes where the solver could handle just about anything, and I was able to employ area ratios that were close to 100. For an area ratio of 100 with a surface quad, your worst maximum included angle would probably be around 178.9. So it's very dependent on your solver there. Now, that being said, that's all about the stretched cells along the boundary of a domain. Let's say you're trying to save cell count in the interior of the domain, far away from the boundaries. Another technique you can use to help save cell count is to go to grid solve attributes for that domain, and you can increase your maximum equilateral edge length for the domain. When you increase that value and you decimate the domain, that will remove interior points from the inside of the domain and create larger cells in the interior. Now, that being said, you need to be aware that by hitting the decimate command to remove those cells. That would also clear any T-Rex layers if you're using T-Rex layers on the domain. If you are using T-Rex layers, you may want to use initialize instead of decimate, which would also remove those interior cells but maintain your T-Rex layers. Okay, so let's go back to our questions. All right, can two sources intersect? You can have as many sources as you want in your mesh. They can be independent of each other in space, or they can overlap. And when they overlap, Pointwise will use some algorithms to determine which areas of which source have greater influence over the volume mesh if they are significantly different. So yes, you can have overlapping and intersecting sources. All right, are there cases where Delaunay is preferred over an advancing front algorithm other than one failing? In general, from what I've seen in our testing, I actually prefer advancing front and advancing front ortho over Delaunay in most cases. And really advancing front ortho is the one that stands out. The predominant reason being we have seen improvements in solutions from Delaunay to advancing front ortho just because the cells are boundary aligned, and if your geometry has boundaries that are somewhat flow aligned, that can give you more flow aligned cells, which can reduce numerical error. So yeah, the only times where I've sort of reverted back to Delaunay has been if I had an issue making advancing front ortho working for a surface. All right, can we see a cut through the source cells? If you have an initialized volume mesh and you create an examination cut, it will go through those source cells and show the additional concentration of isotropic tetrahedra there. All right, last question. In the case of a T-Rex block extrusion from surfaces that form an acute angle, and I mean less than 90 degrees, we often will get bad cells or extrusions from walls. How can we handle this? Supposing that we don't want to create structure blocks on the walls. Okay, so there's a couple of approaches to this. So the first thing I would do is whenever I am creating a volume extrusion, a T-Rex volume extrusion, out of an acute angle like that, one of the predominant reasons I see that there's failure or that it performs poorly is if there is a large area ratio coming out of the corner, or the cell types are very dissimilar. So that would be the first suggestion I was making, is if you have a corner case like that, that you make the cell shapes and edge lengths, the sizes, the spacing constraints out of the corner as similar as possible, and that will help you get the best possible result out of the corner. Some of the other things that you can do to improve the mesh for a T-Rex extrusion out of a corner are you can increase your collision buffer. The collision buffer, traditionally people think of it as I have two opposing fronts across from each other and they're going to run into each other. Well, you know, with an extrusion out of a corner, you have two fronts side by side that are growing out, and they can sometimes collide and there not be enough room to insert a good quality isotropic tetrahedra, and that can result in a poor quality cell. So oftentimes if I have some really tight corners, I might bump up my collision buffer in the T-Rex attributes a little bit. A third scenario that you might run into, and I've seen, is with the mixed cell type T-Rex blocks. If you created a quad dominant mesh first and then tried to extrude T-Rex out of a tight corner like that, we might have problems if it was really tight with pyramids being too close on top of the stacks of hexes coming out of the corner. If those final pyramids on top of the stacks of hexes are too close, then that doesn't leave a ton of room for isotropic tetrahedra, which could result in some skewness. What I prefer to do in this situation, if I have a mixed cell grid, is to start off with a triangular mesh, completely triangular, advancing front ortho. And then in the T-Rex attributes, I use the third option that Travis described, the one called all and convert wall domains. What will happen in that case is it will create stacks of hexahedra all over your geometry using T-Rex, but in those corners that are so tight, it will, instead of converting those to hexes, it will keep those as prisms, which means you're not going to have a pyramid on top of the hex stack, which means you will have a little bit more room, because a prism can go directly to a tet. You will have a little bit more room out of the corner for a nice quality isotropic tetrahedra to transition. So that was the last question. Are there any other questions that you guys would like to ask or that you're concerned about with any of the new features with version 18? Okay, I don't see any more questions, so I think we're going to go ahead and get this webinar wrapped up. I'm going to pass it back to Travis.
Okay, all right. Thank you very much, Carolyn. And thank you all again for attending the webinar. Like I said, there'll be a recording available. You can get to that using the URL on the screen, and then you can let us know if you have any additional questions after the webinar, maybe after you've had an opportunity to maybe look at the recording again, and anything comes up, you can email us at letstalk@pointwise.com. Thank you all very much, and we'll see you in the next one.